Hello everyone, my name's Richard-Bollans and I'm going to be presenting some work that I've been doing with Brandon Bennett and Tony Cohn looking at the semantics of spatial prepositions. So I'm going to avoid going into too much detail, which is given in the paper, but try and focus more on the motivation for the approach that we've taken. So we're looking at modelling spatial language in situated dialogue, in particular for referring expressions. So these are expressions which serve to identify a particular object under some common ground. Spatial prepositions are particularly difficult to model because they exhibit vagueness, both in a seriety sense, where there's ambiguity, the ambiguity is a matter of degree, but also in a conceptual sense where there's ambiguity around which combination of properties is relevant in determining whether a concept is applicable or not. As a result of this vagueness, simple models aren't very useful, and we're not so much interested in being able to label configurations with a relation, but in measuring how well configurations fit particular relations. So I've hinted a little bit at the semantic complexity exhibited by spatial prepositions, but I'll just give a little bit more detail here. So as an example, in the case of the preposition in, we may want to just model it using a geometric notion of containment, but there also appear to be functional relationships to account for. So if we look at figure 1 this is from Garrod, this provides, I think, a somewhat contrived example, but that illustrates the point well. So in A, we may say that the pear is in the bowl, or identify the pear by saying the pear in the bowl, even though it's not contained in the convex hull of the bowl. And we're unlikely to use in to describe the relationship between the pear and the bowl in B. And the suggested explanation from Garrod and others is that this is due to functional relationships that exist between the objects. We look at figure 2 from Bauman and Choi. This provides some examples of the different usages of on and its variability. So looking at these images, we may say, okay, there's some variability, but there's this common theme of this functional idea of support. But I think also sometimes even this isn't the case. On may be used to denote proximity rather than anything else, so we might say something like there is a chest of drawers on the wall, where the wall isn't supporting the chest of drawers. So this complexity brings us to some modelling issues that arise. Firstly, as I've mentioned, that functional features appear to be important and generally aren't accounted for. Secondly, for computational reasons, many features are approximated somewhat crudely, and this can lead to miscategorization or confusion. So as an example, there's the notion of containment, which is commonly modelled using the overlap of bounding boxes. If we use this notion of containment to simply model the preposition in, I think figure 3 shows why this can be problematic. So if we're interpreting an expression using in, like the cube in the bowl, if we're looking at A, we might pick the red cube rather than the black cube. If we look at B, we might generate an expression like the box in the table. So yeah, confusion can arise because of the way the features are modelled. And it may be that seemingly non-salient features provide more context and can help to build more robust semantic models. So overall, we want to try and model spatial prepositions in a more developed feature space. So before getting into the models that we've been looking at, I'll just briefly explain the data collection process. So we conducted experiments using virtual environments to create 3D scenes in which participants performed a couple of annotation tasks. So firstly, we used a preposition selection task where participants are given a configuration and label the configuration with prepositions. And secondly, we used a comparative task where participants are given a description and asked to select an object which best fits the description. So the preposition selection task provides categorical data which we use to train the models, and the comparative task provides typicality judgments which we use to test the models. So in terms of the approaches and models we're comparing, there appear to be three main modelling approaches in cognitive science. Firstly, rule-based models, which generally rely on expert knowledge. This is the approach of many existing models of spatial prepositions and generally provides quite simple representations of the semantics. Then there's exemplar models, which measure typicality of a given instance by measuring its semantic similarity to exemplars or good instances of the concept. Then prototype models, which are based on prototype theory, measure typicality by measuring the semantic similarity to a prototypical representation of the concept. There's also then conceptual space approach, which is in some sense a unification of the latter two, where a region is generated from concept instances and a prototype is assigned usually in the center of the region. So the latter models each rely on a notion of semantic distance, which is commonly taken to be a weighted Euclidean metric in some feature space. And I think there are a couple of unanswered questions here. So generally, how weights should be assigned in the semantic distance, and then for the prototype models, how prototypes should be assigned in the model. I think this also then relates to a sort of issue with its centrality, so underlying the conceptual space and exemplar approach, and to some extent the prototype approach, depending on how the prototype is constructed. There seems to be this idea that the more central an instance is, the more typical it is for the concept. So if you have a cluster of instances representing some concept, then the more central an instance is within that cluster, the more typical it should be. But I think this seems to be an issue for particular concepts, in particular where there's some sort of ideal typical instance of the concept which almost never occurs. So if we think about where the preposition in is used, full containment often isn't apparent, even though more containment should signify a higher degree of typicality. So if you train a model around this notion of centrality, you get typicality which isn't really aligned with human usage. So in figure 6 we can consider some of the collected instances of on from the data collection. The colour here denotes the likelihood the configuration was labelled with the preposition. So yellow means they were always the configuration was always labelled with on, and purple means the configuration was never labelled with on. We can sort of see a general trend that on is correlated with support, and as well as the degree to which one object is above the other. Notice, however, possibly separate cluster where this aboveness isn't really apparent. So this is likely the issue of polysemy, which we discuss in a forthcoming KR paper. A term is considered polysemous when it denotes multiple distinct but related meanings. But for the moment, let's just consider support. If we suppose that the best instances, which are in yellow, are exemplars for the preposition on, we get the exemplar mean that's shown here. If we suppose that all the labelled instances represent the conceptual space, then we get the prototype for the conceptual space, which is given here. And I think we can see this notion of centrality in action, and it's not really what we want, as we expect on typically to express full support. The generated prototype, which is shown here, is from the model we constructed, and while it's still not perfect, it appears to me moving in the right direction. So to briefly explain our model, we use the same feature space for every preposition, so I think 9 or 10 features, and we use a simple linear regression to generate prototypes and weights for the feature space for a model based on prototype theory. And details of this are obviously given in the paper. In terms of results, here we compare our model's performance in the comparative task to the exemplar and conceptual space approaches that we've outlined, as well as some rule-based models. So here the simple best guess and proximity models. Details of these are also given in the paper. We can see that our model, which is the blue column, performs better overall compared to the other columns, so this can be seen from the final two sets of columns. Though for some individual prepositions there's still room to further improve our model to perform as well as the alternatives. Okay, so in terms of future work, in order to extend what we've done, we need to account for the polysemy that some of these terms appear to exhibit. We seem to have accounted for this to some degree, and we explain this in a paper at this year's KR conference. I would also like to explore more precisely the relationship between categorization and typicality, and I'm looking at a slightly revised experiment in order to do this. Thank you all for your time, looking forward to any questions and comments.